Okay, welcome everyone and good afternoon. This is the second of many different webinars with our Connected Fleet Challenge webinar series, and we're glad that you can join us today. We're very excited for the work that's being done, especially in this space, and the speakers that we have that are going to be describing some of their lessons learned and sharing their knowledge about what it's like to connect your fleet in the CV world. And so as a reminder, the National Operations Center of Excellence, or NOCO, works to transfer knowledge for the transportation systems management and operations community. And we do this by sharing resources and supporting the TISMO community. Please feel free to browse all of our resources on our Knowledge Center and our website. And if you subscribe to our website for our newsletter, you'll get the major TISMO announcements, including the results of the second TISMO Awards, second annual TISMO Awards. The links to even the Connected Fleet Challenge website, webpage, and also the CAT Coalition webpage is up there on the top right with useful links and a few other links from our website. And for this and every webinar, we record it, and a recorded version of the webinar, along with the presentation slides, will be available within about a week in the on-demand learning section of our website. And so if you have a question, please place them in this question pod here. And those will be answered at the end of all the presentations. And I just wanted to let you know, when you go to the Connected Fleet Challenge link, this is what you're going to see, and you can see already that the resources have been populated. So with that, I am going to ask Blaine to get us going as far as describing some of the genesis of where the Connected Fleet Challenge is, and the other great speakers that we have are Jay Parikh from CAMP, Bob Roush from TransCore, and Rob Zimmer from Panasonic, that are going to be here sharing their insights and their lessons learned. So with that, Blaine, why don't you go ahead and get us started?
Okay, sounds great. Thank you, Patrick. You can see on the screen the agenda that Patrick just went through. We certainly appreciate Patrick and his staff at the National Operations Center of Excellence for helping us host these webinars and doing all the technical things that are necessary to get this up there so that you all can participate. And we appreciate all of you taking some time today to participate with us, and we hope we've got we're sure we've got some good information that'll be useful as you move ahead with the Fleet Challenge. So just as some background that I'm sure everybody knows, the SPaT Challenge has been around for several years. And the original concept of the SPaT Challenge was to encourage agencies around the country, states and local agencies, to deploy PSRC on corridors so that we could all learn how it works and broadcast SPaT and MAP. Many of us have gone beyond that and done more than just broadcasting SPaT and MAP. This is a map that shows all of those entities that have accepted the SPaT challenge or have deployed and are operational with the blue dots. And at last count, we believe we've got about 47 locations in 27 states with almost 700 RSUs operating and over 3,000 planned for operation and almost 10,000 vehicles planned. Many of those, of course, are in the three CV pilots. There are resources on the page that Patrick talked about, and if you or an agency you're working with or a part of are not on the map and are planning to do something related to the SPaT challenge, we would encourage you to click on this link and provide us some background information. Over a year period, we did about 10 webinars related to the SPaT challenge, talked about a broad variety of things, and now we've started focusing on the Fleet Challenge and doing some webinars about the Fleet Challenge. This is the second of the planned webinars. And as Patrick said, they're all being recorded. The idea is that after an agency has deployed some PSRC units along the road to broadcast SPaT and MAP, the next step really is to get a couple of fleet vehicles out there that can receive those messages and see if those messages are received well and have the vehicle broadcast a basic safety message back. So the essence of the fleet challenge is we would, through our own fleets or with partners, deploy at least one light-duty vehicle and one heavy-duty vehicle with an onboard unit, which is broadcasting, which is receiving the SPaT map and broadcasting that back. So that's really the intent, and so that's what these webinars are trying to help us with. So here's the website for the Connected Fleet Challenge that talks about how to do that, that talks about what the challenge is, and you'll see off on the left-hand side a bunch of tabs which will take us to a variety of parts of the Fleet Challenge. If you are participating in the Fleet Challenge, what we ask that you do is fill out this page where you provide us with name and location and a little bit of detail about the fleet you're connecting. Our intent is to have the map, and I'll show you the map in a minute, have some details so that someone could search the data and say, I'm looking for somebody that's connected a snowplow or a delivery van, and maybe even get it a little more refined than that, so that as we are all doing this, we can pull from expertise of the others who have already done it. So this site here allows you to put in some of that information so we can start building this database. Here's the map. It's unpopulated at this point. We haven't started putting any of the sites on, but that's what it'll look like on the website once it gets open and running. So we've also started collecting and assembling a bunch of resources, documents that talk about how to procure the equipment, how to install the equipment, et cetera, et cetera. And this resource page is already being populated, has been populated with a bunch of documents. So we would encourage you to go to this page on the site and start looking at procurement documents and reports and various things that we found and we posted. We also encourage you to share with us other documents that we could put onto this site and help people move this forward. So today's webinar, as I mentioned, is the second in a series of 3 specifically focused on the Fleet Challenge. The first one was back in October. The third one is scheduled for that first week of January. I think it's the Friday right before TRB starts, if I'm not mistaken, on the calendar here, or the Thursday right before TRB starts. So we haven't built the agenda for that one yet, but stay tuned, and we hope you'll all join us again for that call. So with that, we will move on and I can't remember who the first presenter is. The first presenter is Bob Roush from Transcore, I believe. And when our presenters are done, we'll do some Q&A and talk about all of the issues that are brought today. So, Bob, if you want to take it away now.
Thanks, Blaine. Let me see. I think I can now make this thing go. Nope, it just moved off a little bit. I'm going to talk a little bit about what we're doing in New York because we are working with fleets. It's not just put out the RSUs and SPaT challenge. Hope they will listen. We actually have to go on the whole side of the fleet. And I'll talk a little bit about our project and try to give you some over insights and lessons learned from our rather interesting fleet deployment to date. Let's see if I can keep this thing going. Our goal has been thousands of vehicles, and right now we're up to little over 800 as of yesterday, as a matter of fact. We are actually trying to outfit a wide variety of vehicles. In our case, it was a procurement of a custom OBUs, onboard units. We refer to them as ASDs. And we plan to have about 500 RSUs. We're up to about 300 so far. And I won't talk about those, but we're upgrading our controllers. We're using the 1202V3 SPaT, and we're streaming SPaT map also to an Amazon web server so we can do pedestrian apps. The important thing to remember about the project in New York is that it was the goal of the project was actually to see how well things my thing is very sensitive here. See how well things reacted to where am I going to make that, to really test what it would do or how the connected vehicle technology worked in the urban environment. These are our applications. Now the top of the ones in blue are the usual applications you've seen, but there's a number of other applications that are more V2I focused that we're actually trying to do. So the selection of what we're doing with the vehicles right now is focused on those V2I applications. But more importantly, on the bottom, we had to introduce a number of applications that were related to how you operate and maintain both the fleets, the fleet of vehicles, track what they're doing, as well as the system aspects. The project area, as it were, is right in the heart of Manhattan, and we're also got a piece in Brooklyn, so we're experiencing a whole lot of issues. The purple lines are brought in things we had to install afterwards to improve our location accuracy. There are additional RSUs that we support for the triangulation. So that's sort of an overview of the project. We're moving forward now with our fleet deployment. But I'm going to talk about three things today: practical data collection, what we've been going through with the onboard units, and some of the security aspects. And now, because we specified, or we're specifying the units, we went through a complete development of what we wanted to do in the back office or with the data collection. We had to make sure it was both scalable, that it would address any of the constraints of our backhaul, that we were more interested in retrieving information than raw data to leverage, and we can leveraging our edge computing devices, our OBUs and RSUs. But one prerequisite for our project was that it lived in the DSRC environment. If you look at what's been going on in the demonstration projects and safety pilots and others, they've been collecting every BSM, every SPaT, every map, every TIM message heard by everybody from everybody. And that winds up generating literally gigabytes of, per hour, terabytes per day, and it's just not practical with a wireless backhaul. So we went back to reanalyzing our data needs and addressed how we would collect this data, because the data collection is what a lot of this is about. Let's see if I can get this to advance here. Our data collection was needs driven. I'm sorry, I'm having a problem with my computer today. It was needs driven. One of the prerequisites of the pilot projects was to actually be able to measure or quantify the benefits and the issues, as it were. So we developed a whole series of actually 47 performance metrics, and using the performance metrics, we then developed our data collection, data collection program, which it really, rather than just collect all the BSMs, we in fact were doing we set down to collect event data logs. These are all in our device procurement. You'll see a little more detail to collect all of the relevant data for each individual event. That's an alert, a warning, and before and afterwards. Then we provided some customized event data collection for it. We have the ability to store it, encrypt it. It has a limited lifespan on the vehicle. And then we collect all of this data over the air from the OBU to the RSU using the DSRC communications. So that's our only means of collecting the data. The data itself is obfuscated aggregated, so it is no longer decipherable into PII. We also are collecting RF logs for operations and management support, and that is the OBUs collect the first and last BSM, first that they hear from others, the first and last SPaT and map message they hear from every RSU, and the RSU in turn collects the first and last BSM it hears along the way. From this, we pushed on the edge computing to collect travel times at the remote communications unit, and at the RSUs, And what it does is it looks at and determines when one of these devices crosses into an intersection, relays that to a TMC so we can compute it. So the alternative here is it gets us a whole lot more data without sacrificing the volume of raw data it would take. We actually are collecting about 2 BSMs per vehicle while it's in range, rather than the 600 per minute we would collect to actually do this kind of computation. In the event records, we collect a short period of time before and a short period of time after. Basically, it's about 10 seconds before and 10 seconds after, depending upon the type of event we're trying to track, or up to 180 seconds before and after for things that may want to deal with what happened for the intersection cycle. When we looked at all of this, this provides a practical mechanism for data collection. This gives you another picture of what it is that we're collecting. The actual onboard vehicle unit collects the BSMs it hears from the couple of nearby units, so those that are within a region of interest, and then in its own BSM, as well as any SPaTs and maps it hears from the closest intersections. And then in turn, it also captures all of the parameters that triggered the alert. So from this, we can analyze the alert we got, what happened, and why it happened. Is this going to advance? Yes, it is. In our procurement documents, we included concepts of the data we wanted to collect. And if you look at what's going on the onboard unit, this is sort of a rough flow chart for the collection of the pieces of data. So we're keeping a 5-minute rotary buffer, which gets us the before and after, actually up to 300 seconds. We collect all the RF data, and then the other devices we see in the breadcrumbs, one of the other things we collect is from the system status log. We'll collect start time, end time of trips. We also collect uptime, GPS lock, and any issues we have with the software. The data collection is uploaded, and here the uploading is done so it's secure, and the various colored dots, this is a concept that was put in the specs, and the vendors have built it. Our log files are created as a record at a time, or as it were, and then each record winds up being compressed because we have a limited bandwidth in our backhaul. It is then signed so we can guarantee the integrity, and then we guarantee its delivery. We don't want to lose any data. So what you're seeing on here is the concept that was put into our procurement document that ensured that the OBU and then the OBU-RSU combination collected what we needed, and that it got through to the end, to the TMC intact, that is, and that we didn't lose any data. That we had to protect the data from its privacy, and after it is uploaded, as I said, the data is normalized, obfuscated, and aggregated such that you cannot disaggregate it. It's not stored in its raw forms. BSMs could be used, and we didn't want that, so we make sure that the BSMs that we are saving cannot be used to recreate accident scenes. If you think about it, if you collect every BSM at an intersection, merge that with the police records, you can tell exactly what the accident was, who was at fault, and why, and that was not data we wanted to make sure we had. The data is only associated with the vehicle. We don't have any idea of who's driving the vehicle. And the system tracks the units just to make sure that the software updates are right and that the general usage, and make sure that we don't have any that wander off. Can you advance the slides for me here? I'm having some problems with the advancing. This time it did, but it's not always. To give you an idea of what we can do with the data, what we are doing with the data that we've been getting so far from the RSUs is the first and last. Now this is where around our office in Queens. Actually, it's around the city's office in Queens where the RSU is. We are actually getting data from up to 1,100 feet away, 1,100 meters away, 500 meters across to the bridge. What we're seeing is the range is much bigger than the 300 meters we would have expected. But you can also see that where it is, you can see that we collect vehicles up and down the avenues. If I go, I've got a couple other slides here if they advance. We are now using this data that we collect from the RSUs anyway, from the OBUs, to determine what services we're going to provide where. Now, I'm going to go a little bit on the services because we have to deal with the over-the-air downloads and uploads. So by using the data we're collecting, we've been able to actually determine where we want to park it. Here's an example in Manhattan. The little triangles, as it were, are all where we've got RSUs. The ones here were not operational. The city's been installing a new communications network, and we're just getting those online now. I'm going to look at some of the onboard unit and configuration considerations now that we've gone through. That's data collection. Now, in the onboard unit, you'll have to advance the slide, I guess. Can you do that? All right. Our procurement was done through the OBU was an open specification. Now, we addressed all the applications from our ConOps. We addressed the logging requirements from our ConOps. And then we used portions of the safety pilot in-vehicle device specifications, worked with our stakeholders to make sure that we had all the performance measures were being collected on the vehicle, worked with the fleet owners to address any of their concerns and data they wanted, and then their requirements, one of their requirements we had for our OBU was that we not have any display. The specifications that we put out for our procurement of the in-vehicle devices included a complete installation kit with antennas, data cables, all the cables that are connected to the CAN bus, mounting mechanisms, and so forth. And we identified in our procurement the security requirements. Some of the things to consider when you're buying an onboard unit were the power down considerations. Everybody says, no, you can't draw any power when the ignition's not on. Well, that doesn't quite work right. So we wound up specifying the minimum power requirements, quiescent power requirements, which are within SAE standards. We are very concerned about watchdogs, and we don't want to have to touch the vehicles. So I'll go a little bit more on that a little bit later slide, but this was an experimental purchase process which can be very difficult to manage. But we're buying thousands of units, and we had to go through the normal process. We identified the over-the-air requirements. If you go to the next slide, our over-the-air considerations that we took on looked at multiple mechanisms for how we would collect the data and deal with downloads. DSRC was sort of a requirement for all the pilot projects to use. So we only have two mechanisms that we can use for collecting over the air, either the data or updating the software, and that's DSRC. We can also do that when we connect directly to the vehicle, but because these are fleet vehicles and they're in service, we can't do that. There's a cost every time they bring the vehicles into the shop, and that gets prohibitive. So we established the OTA requirements, and they support software downloads, and we are currently updating the firmware depending upon what additional features we have, whether they're silent or not. We collect all the data that's being collected on board. We get it uploaded over DSRC, and the DSRC service channels are what's used for the SCMS to download our certificates. We developed a network coding scheme, and the way it works is the OBUs actually can accumulate their downloaded image over multiple RSUs until they've got it, validate it, and then store it. Next slide, please. We established security profiles for the messages, the mandatory data elements, and the PSIDs. We have special service permissions, special security service permissions that we've done because we have regulatory speed in our map message. We established the priority with the vendor when it sees the wave service announcement, what goes first. In this case, OTA download is always first. So when the RSU comes by, when the OBU comes by, it downloads first. We had to make considerable adjustments in the urban environment. So you'll hear that in the CAN bus interface. We meet J2945/1 requirements, which is what was the base requirements for all the applications. Then once they get done with the installation, they have to go through a calibration for the navigation unit, and then we verify the installation, the GPS integrity. There's some other issues with in-vehicle mounting, CAN bus interface, and over-the-air. We did a lot of work with over-the-air stability, reliability, and transfer time to make sure that whenever we did over-the-air updates with our devices, no matter what we did, we didn't brick the devices. Next slide. The OBUs have extensive configuration requirements. For each vehicle, make, and model, we actually have to configure so it knows where the antenna is, where all the different vehicle types, all the parameters that make sure that tell the onboard unit how it's to work. This just gives you some flavor for the nature of the configuration we have to do. Next slide. All right. And then this is just more of the same. This is, again, we have an interface to the unit. When you're mounting the antenna, where it mounts matters. Try your antenna mounts and see what you get for radiation. We're using it through the glass antenna in one case. In the other case, it's this classic shark fin. Next slide. Mounting it in the vehicle, we bolted it under the seat. It's securely mounted because if you don't securely mount it, the inertial navigation system won't work. By the way, you have to make a decision there whether you're going to use inertial navigation or whether you're going to use the RTCM correction. Next slide, please. Some of the additional considerations, we had to target our individual groups so we can download particular vehicle groups. Be careful if you wind up drilling. We did some significant vehicle damage because the installation crews weren't using the right hardware in drilling. And the interfacing to the vehicle CAN bus I'll talk about can be tricky. Next slide, please. We wound up using a passive CAN bus interface because there are other devices in the vehicle, and when we go on the CAN bus to ask for the devices, it would interfere. And using the OBD2 port, which is the easy plug-in port, the speed that we're getting, the speed accuracy and the rate at which we're getting it was not adequate. So when we adopted the use of this passive interface so that all of our onboard units actually connect to the vehicle bus. Next slide, please. Our user interface is all visual. We're using tones, beeps, words, text to voice, and stereo speakers. I wish we could have connected to the vehicle audio system, but if we're not an OEM and if the OEMs don't give you all the rules to do it, that's not something you can do. Next slide, please.
Bob, I know security is important, but I'm going to see if you can do it in about 5 minutes for the next couple of slides.
I expect to skip through this quickly.
Okay.
Go ahead. One of the other considerations that you really need to understand is that when you get involved in the security systems, this is sort of a lifespan, as it were, or the life of the security, what it takes to interface to the security system. It starts with your OBU developer. He's got to get his OBU certified. The vendor then enrolls the device in a secure environment from the SCMS security enrollment portion, and then once the device is activated, it goes and gets its pseudonym certificates or operating certificates, and then the device becomes operational. And now, because we are topping off, as you'll see, we have to actually, all of our certificates are renewed once a week, and they start 2 days prior. So all of our units actually go through the RSU to go back and get more certificates. Go ahead, you can advance the next slide. I wish my advancer was working because I could go through quickly. Some things to be aware of. Not all of the mechanisms and things necessary for the security system to be fully operational are currently in place. And if this will go to the next slide. This gives you just a rough idea of the network construct, the security walls, or the security that we actually had to put into place. If you go to the next slide, you'll see this gives you an idea of the different protocols and how the security was managed within the system. Now, the security between the RSU and the onboard unit, of course, uses the 1609.2, the standard SCMS certificates, but it takes all of the rest of this to be able to actually support the security system. So when you're looking at what it's going to take to put security in place, These are the bits and pieces. This is how we did it in New York, but you will need all of these pieces. The ASCC is New York's traffic controller. Next slide. Our certificates only last, I said, 2 weeks. They have to top off every week, and they have both geographic limits as well as the time limits. That has been a real challenge. The next slide, please. Some of the lingering issues just you should be aware of as you look to procuring the onboard units. The pilots are using the SCMS from ISS. That was all arranged by US DOT. Initial behavior detection is under test, but it's not been deployed. The certificate revocation list distribution is just becoming available, but it's not integrated to the security software. The security software still has standards evolving, and not everything is well documented. Some of the standards, some of the base standards are still undergoing changes as new people and other people are coming on with the deployment. In our case, the 3 pilot projects work together to make sure we use a consistent interpretation. There is no current standard for the RSU. Ours was developed based upon what we had in place, and as I indicated earlier. It also depended upon the NTCIP standards, and it depends, the whole design was based upon the DSRC channel availability. Next slide. I think that brings it to an end. And there's been a lot of material, more than I can cover in detail. If you go to the next slide, one more slide, this is the resources that US DOT makes available about the pilot sites, and I can tell you that there's a wealth of information on the pilot sites, from our ConOps documents all the way to some of the procurement documents, the design documents, and all of the evaluations they're doing. I hope that gives you a rough overview of what we've been going through as we deploy, and it's supposed to be as many as 8,000 onboard units. Back to you.
Thank you so much, Bob. And now we're going to bring Jay into our mix to give his perspective, especially from CAMP, and how the verification for SPaT and MAP messages have been going. So, Jay?
Thank you, Patrick. Good afternoon, everyone. What I would focus primarily on the vehicle-centric application called red light violation warning. We've been developing these applications and test vehicles for a number of years now, and have had a chance to test many of the deployment or intersections around southeastern Michigan. And I'll talk about what are our findings and what are the tools that we have to develop to make sure that the SPaT and MAP transmitted at those intersections confine and conformance to the standard, as well as the needs for the application, which is red light violation warning. So with that, what I'll talk about is why do we need a SPaT and MAP verification? What are our preliminary findings when we started testing our test vehicles along the intersections in southeastern Michigan where we deployed SPaT and MAP? That led us into development of a verification tool, and further testing that we conducted using the tool, and what are our findings are, and the recommendation for any particularly actuated intersections. So in order for the reason why we need to have a SPaT and MAP, so that vehicle manufacturers, as you know, are embarking on productionizing the connected vehicle technologies, and one of the applications is called red light violation warning. So we would like to have the intersections communicate properly and interoperably, basically, with the vehicles. This will also help deployment of SPaT challenge initiatives in terms of if we have the verified intersections, and we've been talked about a number of times, that how do you know all these intersections that's been deployed under SPaT challenge, how do you know they are all verified, and what is the process of verification, and what is the minimum requirement for verifications. We also would like to make sure that all the information transmitted within SPaT and MAP meets the SAE J2735 specifications. and the data and the valid required data elements are properly filled in those message transmission. So with that, what we started doing out is using a test vehicle to drive around at deployed intersections and collect data and observe what's going on. That was a kind of a burdensome and unsafe practice, primarily because you have to drive through each and every lane to see if I'm getting mapped correctly, SPaT information correctly, which matches with what I receive and what's been transmitted. And many times we have to stop and observe if the signal head is actually changing the phase information, which matches with what's received in the vehicle as a SPaT information and so forth. It's a time-consuming and error-prone process. We also, during those process, we figured we ran into several situations in which we found that when a SPaT and map is transmitted, application didn't do any good and did not work. And it found out that when those two messages are transmitted, the intersection IDs are not correlated, meaning they're different in the same for a same intersection. So application did not know what to do with it. Similarly, in cases we also had experience that an intersection was partially mapped, meaning out of 4 lanes, only right 2 lanes were mapped. And if you were to drive your vehicle on the left 2 lanes, we don't see any information coming out, and it looks like the intersection is not working. And turned out that, yeah, the maps were missing. In some cases, we also learned that an RSU was using pedestrian crossing phase and time information and sending it as actual phase and time information for the intersection, which caused different problems, and we started getting flashing red ball instead of actual phase information. So there were a lot of things that were not properly transmitting the information, and the conversion from a controller to the SPaT message and received SPaT message, they were inconsistent and incorrect. So all these things brought us into development of a tool, so we don't have to spend an awful lot of time figuring it out what actually intersection is doing. So what we did is develop a handheld portable tool which consisting of an OBU and a tablet which actually becomes which is actually a device on which a visualization is shown about the received SPaT and maps. So OBU receives the information, it converts that packet data to and serializes its information as per the J2735 to a proper values, and that value is transmitted over Bluetooth to a tablet, and tablet overlays that information using Google Map and shows you what's the current value of the SPaT information, including an icon that shows what the current phase information of that intersection is, or that particular signal head, and you can literally watch that it turn its phase when the time runs out, and that you can watch it against its visually watch against what's transmitted as a phase information and time information. And it also shows the map of an intersection is overlaid on top of a visualized satellite view of Google Map. So this helped us evaluate intersections, performance, and verification much quicker and much better, and it also allowed us to both visually see the information as well as collect the data for post-processing. So this particular is a very handy portable device with a mag mount antenna, DSRC. We put it on the top of a vehicle with the OBU turn on and activate the application on the tablet. You don't have to drive through intersection. You stop at an intersection nearby where you have a DSRC range, so you can receive all the messages from all the directions from that intersection, and it shows you all the information simultaneously. So now let me move on to using this tool, what we have discovered as we did some testing. So in this particular case, this shows you what are the things that you can test using the SPaT and map for SPaT and map conformance using this tool. As I mentioned, you can visually verify certain elements, and also you can generate a report as a post-processing to see exactly what's going on. One thing is not capability of this device is that we cannot actually verify that what is actually produced by the signal controller is the same information is translated for the SPaT and the same information is received by the vehicle. That piece is still missing and is not doable through using this test tool. That requires additional information coming out directly from a controller. Moving forward, let me just touch upon a couple of scenarios that we experienced using this tool and data that we collected and post-process. Again, our application and verification and testing for this using this tool was focused around a red light violation warning. What is required for an application to perform as intended? As far as we see that, yeah, it is conforming to the intersections that we tested, conforms to the J2735. The data elements are populated as required by the standards, and all this information is right. However, the behavior of some of those actuated signalized intersection were kind of conflicting in the sense that the piece of information that's coming out from SPaT, which is supposed to provides two pieces of information. One is the phase information and the time information, and there are instances under which those two are not correlated, which makes it difficult for the onboard application to how to interpret that information and what action to be taken as a part of the algorithm. So this is what I'm going to focus on it in next couple 3 slides. So in this particular case, what we have observed is that when the mean end time, and which is a part of the specification, provides the information about the current time and how long will it take before the current phase will change on a particular the main artery. It's a very large number, around 3,000 seconds. However, when a pedestrian crosswalk button is pressed and or the pedestrian crosswalk goes into don't walk flashing light, that number dramatically drops from some large value to 10 seconds, which has been programmed by the controller. And at that point, it starts counting down to the point and that phase changes. So the sudden drop in a number from a large value to a small value may confuse the application, and also sometimes depending upon where the vehicle is along the lane and near the intersection, certain pieces of information may provide incorrect behavior to the application. Similarly, what we have observed in a scenario, so this is what's happening. So as I mentioned, it starts off with a large value, it drops slowly counting down, and as it reaches a certain point when this actuation takes place, then it drops to suddenly a 10-second value, and then it changes, the phase change takes place. In this particular case, what is happening is that actuation can take place at 2 different levels. In one case, if it is on a main artery, the vehicle detection, which increases the passage time. But during that time frame, as you can see here, is the time starts at the mean end time set to like 20 seconds, then it goes down to 0, and it goes into green rest mode. Phase does not change, it remains green. When there is a passage time is actuated by the vehicle on the main line, it goes back up to 2.8 seconds and goes back to 0 again. So at this situation, the mean end time value keeps on changing 0 and some defined value, and it fluctuates between those 2 values. However, the phase does not change. On the second level of actuation, if there is a crosswalk button is pressed along minor street or the cross street, or the vehicle is waiting to change, gain an access to the green signal, then again the mean end time value goes up to 12 seconds, and then it counts down. At that point the actuation takes place. So you can see at two different locations the value of mean end time can keep on fluctuating, and that is information that we receive as a part of the applications on the onboard. Application may get confused about it because the time has expired, however the phase does not change, and time goes back up again to some value, comes down again, and such forth. This phenomena, we have seen it here in Michigan, as well as talking to other colleagues in California. They have seen the similar kind of behavior at an actuated signals. So these two things I wanted to point it out, that this is where we see that the behavior of an application could be very erratic, in the sense that the application does not know what to do under those conditions. So what we have been proposing, and this is just one of the proposals from our point, is that instead of this value that keeps on going up and down, why don't we have a mechanism through which the values can be held, because controller does not know when the phase is going to change, depending upon, because it's receiving an asynchronous input from either the cross street or from the main street. And under those conditions, until it is ready to actually change, the timer is ready to count down and change the phase, hold that value to some specified value of end time, so that the timer does not go to zero and the phase change occurs when that hits the zero value. So this is the proposal that we've been talking about, and would like to get the feedbacks from the IOs and implementers. So this captures our end of what we have been doing in terms of verifying and testing intersections along in the southeastern Michigan areas, and also using the test tool, and also what we are observing, that is how we can get this to the point where the application does not get confused about it due to the information that's coming out as a SPaT and map. They cannot be correlated easily. So with that, that's my presentation here. I'd like to introduce the next person, Rob Zimmerman from Panasonic.
Hello, thanks. Appreciate the introduction. Again, this is Rob. Just bear with me for a second while I share my screen. And can someone confirm you're seeing the full-size slide deck?
Yep, you're good to go, Rob.
Excellent. Well, thank you very much for the introduction. Again, my name is Rob Zimmer. I'm the Director of Cirrus and VDEX Deployment Solutions at Panasonic Corporation of North America. Really appreciate the time to talk to you all today about the Fleet Challenge and some vehicle deployment lessons learned. Today we're going to talk about, first of all, who am I and why am I here talking to you about this? Second of all, why you might want to engage your fleets with VDEX technology. And then lastly, I'd like to report on some lessons learned from some of our deployments, some things to pay attention to if you're going to go after installing VDEX technology on your vehicle fleets, because there's definitely some critical aspects that we've learned to help the process be as smooth as possible. So first let me address the question of what you might be thinking is, why is some guy from Panasonic, a company that makes TVs and batteries, talking about equipping vehicles for V2X? So our corporate mission is to improve people's lives and make the world a better place, as expressed in our brand promise of a better life, a better world. Making automobile travel safer and more enjoyable, reducing accidents and fatalities, mitigating congestion, and helping to protect the environment are opportunities that are very much keeping with what we've always been about at our core. So very consistent with our methods previously. You probably already know about the Panasonic name from microwaves and cameras and TVs and blow dryers. But we've been actually moving more into the business-to-business environment and business-to-government environment. In particular, when it comes to VDEX, really helping our partners in-state governments deploy VDEX technology on the roadways to make roadways safer and more efficient. Most recently, we've deployed 100 OBUs in Colorado and 100 RSUs across 90 miles of Interstate I-70 into the mountains. As part of that deployment, we produced with our partners the first production-grade cellular V2X OBU, built, tested, and deployed on 100 fleet vehicles with CDOT. We have the first production-grade dual-mode cellular V2X and DSRC RSU, built, tested, and deployed in 100 locations, and this device is software configurable to be either DSRC or cellular V2X on that roadway, so no bucket trucks to convert those. And then finally, really the focus of Panasonic is building the next generation traffic management center software solution, which we call Cirrus by Panasonic. We've built and tested that product and scaled it to be able to consume 100,000 simultaneous vehicles in range of RSUs to support the use cases for V2X. So that's really where our focus has been on V2X technology here in Colorado and why I'm talking to you today. So we'll move on now to why you might want to equip your vehicles. So why would you want to do this? There's really two main reasons. One is to start equipping your fleet to understand what is this new data source, understanding the flow of data into the TMC so we can begin to anticipate the use cases and applications that this data can provide. Really what BSM data and pro vehicle data from vehicles is really has a chance of revolutionizing how we're managing our roads. And we're really seeing this as an opportunity for state and local governments and entities to start building up their fleet knowledge and building up the understanding of what exactly is this data and how we might use it. The other reason is the standards do allow some fleet management with this technology using two-way communications that provides some identifying information in a fleet environment that's similar to AVL systems, but may have benefits of a single system that can consume that data and also manage fleets. This really allows for high-fidelity data collection, which is going to basically provide insights such as near real-time crash and incident detection, hyper-localized weather data, intersection movement data, as well as volume, occupancy, and speed data collection. And of course, there's endless other opportunities that could be seen for this. So we keep talking about data. What data? The SAE J2735 standard really outlines the message set, but we need to populate that message. And that data can come from cars. Today's cars have a lot to say, and this source of detailed, context-aware data will be critical for managing our roadways safely and efficiently. If you look at this graphic and you see all this data on this kind of outline of the vehicle, x-ray of the vehicle, you might think, not all the vehicles on the roadways have this kind of data. And 10 years ago, you would have been right. But today, most vehicles on the roadway have most of this data available on board. It's a matter of getting at that data and providing it as part of a message set to really enable the capabilities of V2X. So we do that, as I mentioned earlier, with the basic safety message, the SAE J2735 basic safety message. And for participation, all vehicles must broadcast this at 10 times per second. These messages enable safety-related applications on the road, but also add critical context to what's happening. Things like steering wheel angle, acceleration profiles, and airbag status. Way more than you can get off of traditional sources of data coming off of your smartphone that you carry in the vehicle. Working with OEMs to access this data has been a critical piece of the puzzle. And we've been working with OEMs, including Ford, to gain access to not only the core data, but also the Part 2 data, which really adds context to what's happening. Adding this Part 2 data to the broadcast really lets DOTs consume this data to understand what's happening and have context for what's happening behind events happening on the road. So continuing on why you should equip your vehicles, another reason is to better prepare to communicate with vehicles on the road. Once you're consuming data in, you can understand what's happening. That allows you to communicate to better situational awareness. It might be situational awareness for roadway operators and first responders. That's generally through cloud-based data analytics, TOC, TMC systems, such as Cirrus, but also get messages down into the vehicle. Vehicle operators are in the best position to make good or bad decisions depending on the environment. So we want them to have just-in-time, where they are information, allowing them to make better real-time decisions to avoid secondary, tertiary crashes, as well as to understand what's happening on the roadway in front of them, maybe beyond line of sight. Of course, I mentioned AVL as a potential use case. As I mentioned, the standards do support some identifying information as a DOT fleet when you own that fleet. And really, once you can enable vehicles for that, it really opens up a bunch of other additional applications. Thinking here, enhanced maintenance decision support systems. If you have equipped plows and you have micro weather data from vehicles running around the road or weather sensors, you can really make some really critical decisions for plow redeployment and re-engagement. Signal priority and signal preemption are also use cases where you can actually approve your fleet vehicles' priority or preemption of signals in order to complete their missions more efficiently. This really gains a lot of advantage because we're looking at one technology that can support all these use cases instead of having multiple technologies running around in the vehicle. So that's a lot of the reasons why you might want to equip. I'll talk a little bit about what's important when you equip. These are taken from lessons learned from our deployments with state DOTs, showing a little bit about some of the challenges and some of the opportunities that we've found. The critical one that we found for deploying vehicles as you're engaging fleets is that you need to understand schedule and have clear accountability and expectations. DOT fleets are busy. All vehicles are busy, they're expensive, and we want them used to meet the mission. So those fleets also can be even busier than their regular day-to-day jobs during incidents and inclement weather. It's been really critical for us to set clear expectations for the equipment installation process and schedule. We found it really important for us to make sure we're communicating clearly with the vehicle operator and the manager of those people to make sure that everyone understands what the plan is and everyone understands what the benefits of the program is for installation so that it can happen efficiently. The other lesson learned here about scheduling is making available substitute vehicles during installation. The installation process doesn't take seconds. It takes some time, and make sure that the people who are you're taking their vehicles have the ability of getting their jobs done in an otherwise manner. So we've identified that as a key engagement point as you are scheduling and creating accountability. Next, I'd call location, location, location. Geographic location and proximity to vehicle regular service and operational envelope is really critical. We need to make this process extremely simple and easy for the vehicle operators. Let them bring their vehicles in a way that is convenient. So we found that having diversity over locations for install is really important in order to make sure that we can make it as simple as process for the targets, for the vehicles that we're targeting for install. As an extension to location, location, location is the location. The environment you're doing the installs in is really equally important as the actual location on the map. You may find a location such as the one pictured in order to install vehicles, but it's more than just the space. You have to consider environmental concerns. Make sure that the environment is good for the technicians and for the vehicles and for the technology. So make sure that you have heat and air conditioning available in the environment. Make sure that you have protection from the weather elements of rain and snow. Critical that you have enough light in the environment. Critical that you maybe have supportive air if you need that for your vehicle maintenance. Enough power, and of course communications, whether that be cellular or Wi-Fi. All these are critical aspects of the installation location that must be looked at to make sure that you can provide a very efficient process that allows for quick turnover of vehicles to get them back on the road. The goal is to get as many vehicles equipped and back on the road as possible. I share this as an example of something we tried. This location didn't meet a lot of those requirements. We couldn't get an actual convenient location that was indoors and had all those requirements, so we made our own. This was a great location in Colorado for the drivers, but had a lot of limitations and other factors. It worked for us, but I use this as a case in point of lessons learned of make sure you do your homework on the proper location. This facility didn't survive very well in 70-mile-an-hour winds. Next is people, people, people. Make sure you have the right people to do the job. The proper skill set for scheduling, installation, and quality teams is critical. Proper cabling within a vehicle environment is not something any technician can do. You need technicians that have the experience to understand how to take a car apart, how to properly wire it to not cause additional problems, to make sure you understand the vehicle power and data systems to get access to power moding to turn off and not consume power when the vehicle's off, as well as how to get access to that really critical data. The data makes the VDEX system work, and without that highly valuable contextual data set, there's not a whole lot you can do. So it's really critical to do that. In addition, also understanding that every vehicle make, model, year, and trim is different. So having that experience, having that flexibility to adapt to the needs is really critical for a successful install. Next, and probably the most critical thing, but I left it for last, is the actual onboard unit. The onboard unit you use really makes it all work. And you need to make sure that your onboard unit you're deploying meets the standards, of course. SAE J2945 and J2735 are critical. IEEE 1609.2, 3, and 4, of course, are also important. But there's other things to consider as you're deciding on an OBU to deploy. You really need that automotive-grade power management. You want to prevent that vehicle battery drain if at all possible. Make sure that when the car is off, it's consuming a very small amount of power, and when on, it turns on and transitions to an on state very quickly. Flexible CAN integration is critical. You need to customize each OBU to the host vehicle. Having a ability to have a flexible CAN integration that adapts to the vehicle that's in is really critical for, again, getting access to that contextual data. Something mentioned by Bob earlier is firmware over-the-air solution. You need to manage software on these devices. Recalling cars when you're deploying 2,000, 4,000, 8,000 cars is a challenge. You need to be able to support feature upgrades and also to quickly squash bugs and security vulnerabilities as they're identified. Because those are real things in the real world that you need to adjust for. Multi-layered security is critical, making sure you have security of the device, but also security of the messages being broadcast and received. SCMS solution for message verification and message signing is absolutely critical for a secure system. Finally, health monitoring. Remote health monitoring is critical. Understanding that the device is operating correctly, understanding that software installations and updates are installed correctly, making sure the OBU is processing data and sending out BSM messages and processing incoming messages is critical for the health of the overall system. So making sure that you have that basic health monitoring that you can see when things go wrong and basically be able to respond and fix them when necessary. And last but not least, our integration tools. It's fun to install a piece of equipment in a car, but if you can't guarantee it's working, there's not much point to that. So having tools that are able to consume the data from a vehicle and inject data via the DSRC or cellular VDEX antenna is really critical. The video shown here is a custom solution we built to consume a VSM from a vehicle and display very clearly to the text which parts of the basic safety messages are being populated and exercised. So they can go turn on headlights, change the steering wheel, change the gear, and make sure that all of the data is going from the beginning of the process, from the CAN bus, all the way out the antenna as far as a correctly conformed VSM message, but also that meets security. So these are really critical pieces to a successful installation event. All this is to really drive DOT understanding of what's happening on the road. We are working to develop with Utah DOT a solution for the next generation transportation management system. Cirrus by Panasonic is really the way we are collecting all of this critical data to basically be able to take immediate action on critical roadway conditions, sensing directly from the roadside, from those vehicles themselves. It's critical that we have this context-rich data set and that vehicles are deployed in a way that meets all the standards. This is me. Happy to answer any questions here at the very end. I think I'm going to pass the baton back to Patrick.
Yes, thank you so much, Rob, and thank you to all of our presenters, Blaine, Bob, and Jay, and Rob also. We normally do this in the beginning, but I kind of wanted to make sure all the speakers had adequate time, but I didn't really get to kind of give you a full introduction, and so I was just going to spend 2 minutes doing that, and we can go ahead and start going through the question pod. For all of you on the webinar today, if you have questions, start typing them in. You'll see it over here, and you'll see that Bob has already responded. So I just want to remind everyone that this webinar is part of the Connected Fleet Challenge webinar series that's actually put together by the Cooperative Automated Transportation Coalition, or CAT Coalition, that brings together a lot of the folks from AASHTO, IT, ITS America, and OEMs, and a lot of our partners. And one thing that I think Blaine mentioned, but just to make it kind of clear, the whole challenge of the Connected Fleet Challenge is to equip at least one light-duty vehicle and one heavy-duty vehicle by 2021, and to start getting that feel for what it means when you start having vehicles on the roadway, communicating with your RSUs, and how that works. You heard generally some really good lessons learned about what Bob and the New York pilot is getting into, and just kind of the complexities that go into it. You heard from Jay about when we start doing it, we think it's correct, but what does the vehicle see? What does that mean for the onboard applications? And making sure we're testing that to understand the ins and outs. And then we also heard from Rob just a few minutes ago talking about when you are looking at a mass deployment, more than one vehicle, what do you have to take into consideration? How do you take that in? And just understanding all the actual implementation complexities and even testing and verification that go with it. So I encourage all of you to put in some questions. I'm just going to read off. There was one question that came in, so and it was answered, but I'm going to go ahead and just read that off for the purpose of those that may be following just on the phone. It was a question for Bob Roush, but which SAE standard are you using to specify allowable power consumption of the OBU within the host vehicle? And the answer to that is actually the SAE standard J3005-2014. 3005-2014, and it permits the device to draw up to 100 microamps with the ignition switch off. And so the folks in New York with their pilot settled for 25 microamps for the OBU, but it's getting into this level of detail when we're looking at connecting our fleets. So, yes, go ahead, Bob.
Yeah, actually, it's a little more complicated than that. I didn't have time to go through some of that, but it turns out that because of the way things work and the amount of things that may be going on, we have a two-step power down. The ignition switch goes off, but the unit doesn't necessarily stop. They have some power step down, so that if it's in the middle of downloading or uploading, it can continue for several minutes before it finally shuts down to a 25 microamp quiescent current with a requirement for a sledgehammer that shuts it down no matter what after a few minutes. But it was because a lot of things can happen. You're getting into the barn and they shut the ignition off and we're trying to upload, and we're in the middle of an upload process. We sort of had to follow that line of reasoning.
Oh, that's a great bit of insight, Bob. And um, yeah, I think most of us probably were like, oh, we didn't even think about that. So thank you for that.
Another thing that I like let me see, Rob mentioned was mobilization of the logistics involved in getting the vehicles to be installed. And we're at 800, we're going to thousands. And the problem is that getting the vehicles to the place where it can be installed is a pretty complex thing when you're trying to do this in Manhattan and Queens. And don't underestimate it. As a matter of fact, we've had to outfit a portable crew that goes out with a RSU and a pile of OBUs and a GPS repeater and so forth, so they can actually set up the vehicles in their shop. We have an experienced crew that does that to expedite. We're indoor shops. We're not trying to set up Quonset huts, but it does work.
Yeah, and I think those are just additional considerations, especially for the infrastructure owner operators when you are looking at, how do you get your entire fleet connected. Similar to that, there's a question that just came in from Jason Osaki. If your vehicles use a fleet management system that uses the OBD2 port, how's your OBU accessing the CAN bus? And I think this one, we might be able to get each of the speakers to answer because they've had different experiences, and I know Blaine's been working with the transit agency talking about buses, but how about we go Bob, Rob, Blaine, and then Jay? So Bob, maybe your experience first as far as the OBU and how it's accessing the CAN bus.
Now that's a good question, because we started going to go straight into the OBD2 port, and by bifurcating and splitting the OBD2 port, plus the OBD2 port actually requires that you go on the bus to ask for the PID you want. Instead, we don't interface using the OBD2 port. We go straight to the passive device I showed that actually runs the wires through this device for the CAN bus. Yeah, you have to find it and separate the wires, but it's a completely passive pickup. All we can do, unfortunately, is watch what goes flying by, but we get it inside or closer to the vehicle, so we get more accurate speed, because the signals don't all appear on the OBD2 port. And we're getting signals that are faster for our speed. We don't electrically interfere, and we don't have the problem that you stated in that situation, obviously.
Yeah, and then Rob, you guys over with your kind of equipping those fleets in Colorado, and I think as you started in Utah, what's been your experience?
Yeah, I think Bob described it pretty well. The OBD2 port has its own challenges, not only for existing devices that may be plugged in there, but also on many vehicles, the data that we're after is filtered before it gets there. So accessing that data behind that port, a little further toward the electronic control units in the vehicle is really critical to gain access to the data that we're looking for in a way that's reliable and accurate. So we use a custom cabling solution that lets us tap into that, again, behind the OBD2 port for permanent installation, allowing for that existing or future equipment that might be installed by the DOT to still occupy that OBD2 port.
Yeah, these are great points, and from a good question. Blaine, I don't know if you have the answer to this, because it's a little bit very detailed, and I know the vehicles you're working with are through the Utah Transit Agency, but any thoughts, or do you have any insight into this and how they've handled it for buses?
So we've equipped buses and snowplows with onboard units, but we have not connected into the CAN bus system on either of those vehicles. So on the snowplow, all we're doing is connecting to the Force America system that runs the spreader and the plow. On the buses, we're connecting to an onboard computer system that's part of the transit agency's fleet management system, simply to find out whether the bus is behind schedule or not. So we're gathering the portions of the BSM data that we're broadcasting. We're just getting off of the GPS system, just bus location and direction, and speed. We're not tapping into the vehicle systems at all. So our
Got
onboard
it. So
connections
that's an
are
interesting point too. Is for a
fairly
lot of
immature, I guess, is
the
probably a
agencies.
good statement.
Yeah.
From our experience, the OEMs are less than cooperative with trying to help you out here. They don't want you tapping back there, and I don't blame them. And the lessons learned are pretty significant. If you touch the CAN bus, be damn sure you disconnect that battery. We actually had some problems with some cars because we didn't, and all you do is touch that CAN bus, and you can actually corrupt some of the processing units they have on board. It just is. It's not set up, or the whole scheme. Maybe someday we'll see it that there's some minimal amount of data that's made available through some port, but right now that's not the case.
Yeah. Jay, I was wondering if you had any insights from kind of what you work with a lot with the OEMs, but on this particular question.
Right. So first of all, from our application requirements point of view, we need CAN bus data from vehicle. Particularly when you talk about red light violation warning, we need to know the brake information, the speed information, the turn signal information, and so forth. So these are vehicle dynamics are primarily required for all the onboard applications to work as intended, and need those data in a quick and fast manner. So what we have been doing as a part of the CAMP, which is a consortium of multiple OEMs, we do not want to know other OEMs' secret about how their CAN operates. So what we have developed here is called a Netway Gateway Box, which is an interface between an OEM CAN interface, and this Netway Box converts that information to a common CAN definition that we developed here at CAMP. And we use OBU supplier, Denso. They support both the slow speed and high speed CAN, single wire and dual wire CAN interface. So we use that interface to connect that Netway gateway box that connects to the OBU. So now OBU can get all the programmed CAN data through the common definitions, and that's how we implement our applications for the need of CAN information for testing and verification.
Is that Denso box available to non-CAMP or others?
I believe so. You can get that, and they have gone through several revisions, but each one of them they do provide a CAN interface.
I'd also point out that when we've been going the different vehicle type, the different make and model years, man, there can be radically different changes in the data you have to pick up from the CAN bus.
Yeah, Bob, thanks for bringing that up. I was just going to echo that as well. That is definitely a challenge I referenced a little bit in my deck. The data available changes make, model year, trim, and mid-year changes among the OEM vehicle updates. So that can present challenges for getting access to data on light vehicles. That being said, it's also worth pointing out, though, that heavy vehicles have a different system in place, and in many ways it's easier to connect to and easier to find data elements because it's less of an OEM secret and more of a standardized communications infrastructure. So if you are looking to do that one heavy fleet vehicle, that actually might be a bit easier in order to get access to data.
Yeah. We've had pretty good access with the buses as well, because we're outfitting about 600, 700 buses, and that's been working well for us.
Wonderful.
So from the CAMP's perspective, we not only grab the data from the CAN bus from our applications, but what the application generates as an output also goes back to the CAN bus, so that individual OEM can display that information in the instrument cluster, for example, and they can create a different user interface or HMI depending on how they want to do that. So the reason for us to very tightly couple with the CAN is very important.
Those are some very great and detailed and in-depth answers. Just speak to the knowledge that's available on our with our presenters. So thank you for that. I haven't seen any questions come through, so I'll give a little bit of a plug. But then, if you have any dying questions or burning questions, not dying, I hope no one's dying. Burning questions that you want to ask the speakers, please do. I would just like to mention that we are going to be able to post a recording along with slides and speaker bios and information on our website, not only with on the Connected Fleet Challenge web pages, but also on our normal on-demand section of our website also. The links, in case you're wondering, are in the useful links box right under Jay's awesome picture. And I will hold tight for about 2-3 minutes and see if anyone has any other questions they want to ask, and ask the speakers to stand by. I usually don't prepare any jokes, so unless the speakers want to chime in with a joke, but we still have a couple minutes, and I didn't want to negate anyone the opportunity. Sure.
Yeah, there's a lot of stuff that I have on my slides that I didn't discuss, but you heard the others talk about considerations for over-the-air updates. Whatever you're going to put out there in your vehicles, you need to make sure you have a reasonably easy way to update their firmware. I guarantee that the first time you put it in the vehicle, it's not going to probably do what you all wanted it to do the way you wanted it to do it. So you need to make sure you have the ability to, I'll call it tune. Some people would call it fix. Other people would call it enhance. It doesn't matter. You just need a way to be able to change it.
Excellent. Looks like we're not getting any other questions. So with that, I hope no one will mind if we end about 5 minutes earlier, but I wanted to thank let me double check one more thing. Blaine, are there any other announcements or closing remarks that you wanted to make in regards to, on behalf of the CAT Coalition and just kind of this whole webinar series?
Only just to thank the three speakers for some really insightful knowledge and discussion about connecting vehicles. Really appreciate that. We learned from that. And thank everybody for participating today. This was great.
Yeah, and especially from me, I just wanted to thank everyone for attending and just, continuing the effort that we have to transfer our knowledge and learn from each other so that, we deploy faster and faster. But thank you for attending, and on behalf of the National Operations Center of Excellence, the CAT Coalition, and all of our presenters, have a great rest of your day. Thank you, everyone.
Thank you.